Okay, so I want to talk about symbolic, statistical, and causal representations today. And I'm very happy to be part of this AIDA lecture series and part of the LS PhD Postdoc Summit 21. So I want to start with this picture here of one of my favorite books, Foundation of Isaac Asimov. And I want to start with this character of Harry Seldon, one of the most enigmatic characters in the history of science fiction. He only makes one live appearance early in the first book. Nevertheless, people talk about him all the time. He's the main character of the whole series. And this quotation here, I'll read it out. He said, Harry Seldon brought the science of psychohistory, so that's a hypothetical future discipline of science. It's a part of mathematics to its full development. And the individual human being is unpredictable, but the reaction of human mobs or large groups, Seldon found, could be treated statistically. Now, this book was published in '51, and probably Asimov had no idea whether this kind of science would ever exist. But arguably, we've been moved closer towards having such a science. And I don't know if Asimov read the New York Times. Plausibly, he might have, because he lived in New York for quite a while. He may have seen this article, which appeared just 7 years later, and it reported on a new machine called the perceptron over here. And this guy here, Frank Rosenblatt, he demonstrated that the perceptron can actually learn from experience and grow wiser as it gains experience. So learns from data. And he predicted that later perceptrons would be able to recognize people or even translate speech. It sounded fantastic, I assume. And in hindsight, it was probably the birth of machine learning. Now, this was a fascinating time, and around the same time there was another revolutionary development, which was that people understood that computers can do more than just compute numbers. They can actually process general symbols. And in retrospect, one could say this was the birth of computer science, and people were optimistic and thought that the manipulation of symbols in programs written by humans should in principle be enough to generate artificial intelligence. And so at some point, there was progress on problems that appeared hard, for instance, chess or automatic theorem proving. And people started to predict, for instance, Herb Simon, one of the fathers of the field, that machines should be able within 20 years of doing anything a human can do. But then it turned out that in contrast to the seemingly hard problems, problems that appeared simple, such as most things animals could do, turned out to be rather hard, and this came to be known as Moravec's paradox. So initial hopes were disappointed, and the interest in AI went down. Things were quiet for a while until suddenly we had this explosion, you can almost say, of the field of machine learning. It started to boom, and now it's kind of all the same. It's considered AI. And we can now actually tackle these problems that animals can do, that look easy, but actually turn out not to be that easy after all. So I started doing research in this field in 1993. I started with neural networks in my master's thesis, and then I got into statistical learning theory in '94. And I really enjoyed working in this field and kernel methods, but about 10 years later, I started getting interested in causality. And first, we simply use machine learning methods for causality, for instance, kernel methods for conditional independence tests and things like that. But then at some point, it dawned upon me that you can also use causality for machine learning, that it tells us something about machine learning problems. And one crystallization point was this neural network tank urban legend. So this is a story where a neural network is trained to classify tanks, let's say Russian against American tanks, and then they find that it works extremely well. So they want to deploy the system and then test it on another data set, and they notice it works at chance level. And the reason, there are different versions of the story, but let's say the reason is that the neural network has simply focused on a pixel in the background, and all the pictures of the Russian tanks were taken, let's say, on a sunny day, and the American tanks on a cloudy day. So there was this bias from the data collection process, and we've just used this feature, which is feature which is associated with the class label, but which causally has nothing to do with the class label. And I was hoping that if we can somehow make a classifier more causal, then it could be made invariant with respect to this kind of spurious correlations. Now, this is a fun story, the neural networks, and it's particularly fun because the army was doing something stupid. The question is whether we are much smarter now. And it turns out, arguably, maybe we're not so much smarter yet. So object recognition, of course, has seen huge progresses, and by some measures of success, we can reach human level accuracy on some such data sets. We can recognize these cows. But if we have test images where there are things, for instance, the beach or the sea, that in the training set may be negatively correlated with the presence of a cow, then suddenly the recognition doesn't work anymore. And the reason, of course, is that machine learning only cares about correlations. It doesn't care about causality, and it's not asked to care about causality. So we shouldn't blame the algorithms for it. They do exactly what they're trained for, but they don't understand causality. And since they are so much optimized for a given distribution, the systems are not at all robust with respect to even tiny interventions on that distribution. So for instance, if we add a little bit of noise, you all know this phenomenon, to an image, then an image that previously is nicely categorized as a pig suddenly gets classified as an airplane. So our systems are not robust with respect to violations of this independent and identically distributed assumption, and they don't understand causality. And the first person who understood how causality is linked to statistics arguably was Hans Reichenbach. He said, or he postulated, this common cause principle in a book called The Direction of Time. And this principle says that if we find two variables to be causally dependent, then there exists another one that causes both of them, and that explains the dependence in the sense that if we condition on Z, X and Y become independent. So that means that we find two variables that are dependent. There's another one that explains this dependence and that causes both of them. And now that Z could coincide with X or Y, in which we get these two special cases. So with the practical example, if we find that the frequency of storks and the human birth rate are correlated, then it could be that the storks bring the babies. It could be that the babies attract the storks, or it could be that there's something else, such as, I don't know, environmental pollution or industrial development that causes both of them. And crucially now, based on observational data of X and Y, we cannot distinguish between these three things. So we need more knowledge. Now, before I come back to this, I want to generalize this common cause principle. And that leads to something called a structural causal model, a field pioneered by people like Pearl and Spertus and others. And here the idea is we have a set of observables that are the vertices of a directed acyclic graph, G. These are the things we observe. Now in this graph, the arrows, they represent causation. And we assume that each of these each of these observables, which are also random variables, are computed as functions of their parents in the graph and a noise term. And these noise terms, so there's one noise term at each node. These noise terms are assumed to be jointly independent, because if they were not, we would refer to the Reichenbach principle and say, well, there must be an explanation for why they are dependent. So then we end up with a bigger graph. So what's interesting about this is that the fact that these noises are independent and now start spreading through this graph means that they pick up a footprint of the graph topology. So that means as they spread in the graph, you start having nodes that depend on multiple noise terms, etc. And then you can ask conditional questions about this distribution. So you can ask, if I condition on this variable, is this independent of this, etc. And it turns out that the distribution over the axis, the so-called observational distribution, which is implied by choosing a distribution over independent variables ui, this observational distribution satisfies what's called the causal Markov condition, which is a particular set of conditional independence statements. So that means we do have some knowledge, some causal knowledge about the graph structure, but that's not a contradiction to the previous slide, because this only works if we have more than two because a conditional independence test requires at least three quantities. Now, this is one way. This is a so-called structural causal model. This is a structural assignment. We think of this as a physical mechanism that connects this variable to its parents. So it's a physical mechanism that generates dependence between this variable and its parents. So this is something that on the surface generates statistical dependencies, but it's something more fundamental that underlies it, that talks about mechanisms. It implies what's called a graphical model. So if we just look at the observational distribution, we get a joint distribution, and there's a nice factorization of that joint distribution. So we can write the joint distribution as a product of conditionals of a variable given its parents. This quantity here, note, that corresponds to one such structural assignment. So this is another way of thinking of this mechanism, another parameterization. It's not a one-to-one mapping. This thing can be represented by many such things. So those are even more specific. But let's not go into great detail on this. What's crucial here is that interventions in such a system can be modeled by changing such function, changing mechanisms. So we have a language, and that gives then a different distribution. So this is a language that talks about not just one distribution, but a whole set of distributions. And there's a notion of action or intervention in this system. We're not just passively observing and predicting one thing from another, but we can start intervening, we can start reasoning about the effect of interventions, etc. So it's a richer kind of model. I should say, even though this is richer, it's more detailed than a statistical one, it's still just a model. And you could go one step further and you could say, well, actually, I would like to talk about differential equations and causality in differential equations. And you can do that, and that's more fundamental, arguably. I won't go into that now, but I'm going to try to convince you that these structural causal models that lie somewhere in between this sort of physical differential equation modeling and the purely superficial statistical modeling, that they find an interesting spot in between that's going to be useful in understanding machine learning and AI. So let's briefly look at this example. So the two-variable case, I told you before, without additional assumptions, we cannot solve the two-variable inference case. So we cannot tell apart what's cause and what's effect. So let's look at one data set here, which is from the German weather office. It's a data set of different measurement stations in Germany at their altitude and the average temperature over the whole year. So you can see that we unfortunately live in a place that's much colder than Greece. And the higher you get, the colder it gets. This is the highest mountain of Germany. And now you can ask the question, is altitude causing temperature, or is temperature causing altitude? Or maybe it's something else, but let's keep it simple. Let's assume it's one of those two, and we want to tell apart which one it is. So, and if temperature causes altitude, then we would say that this is the correct or the causal factorization of this joint distribution. If altitude causes temperature, this would be the correct one. If this is the correct one, let's say, or if this is the correct one, which it turns out to be, or approximately, then this too would be the physical mechanisms, and this would be just a mathematical factorization. So how do we go about this? How would we perform this inference in practice? Well, if we want to sort of go by the book, statistics tells us there's no causality without intervention, so we have to do an experiment. We raise the measurement station, or maybe many of them. We measure the temperature for a year. We find that the temperature changes. That's an intervention experiment that tells us, actually the altitude does cause the temperature. Now, we might actually, it might even be enough to just do a hypothetical intervention, because I just explained it to you, and probably you imagine, well, if we can raise this measurement stations by a few hundred meters, it's probably going to be more windy up there. The pressure is lower, and somehow my intuitive knowledge or a high school physics tells me, yeah, it seems plausible that it's going to get colder. So even with a hypothetical intervention, you might believe that if you change A, T will change, because you can think of a physical mechanism, P of T given A, that you apply, and that applies independently of how you choose the altitude. And that mechanism, you would also believe, should be invariant, for instance, across different countries in similar time zones. So this is a physical mechanism that generates this dependence. And I'll show you a second example before we get a little bit more mathematical. And this is an example from visual perception. So here we have a thing called the Berhard chair. And now whenever our brain perceives something, there are implicit assumptions going on. And I would argue one such assumption is that the brain assumes that the object in the world that we're looking at, and this is an object, even though it's called a Berhard chair, it's not a chair, it's an object consisting of these two pieces. So the brain looks at the world and assumes that the objects that we're looking at are independent of our process of perception, and in particular of our viewing direction. This is sometimes called the generic viewpoint assumption. And if this independence assumption, which we can maybe phrase more generally like this, if this independence assumption is violated, for instance, by looking through this specific hole here, we see an object which in reality is not there. So that means perception fails. So that in the normal mode, perception relies on this assumption, and it's a good assumption, and perception works. So let's assume that the causal generative process is composed of modules that do not inform or influence each other. So again, sticking with the two variable case, let's assume we have two variables x and y, and let's assume there's even no noise. So x is the cause, y is the effect, but it's just an invertible function of the cause. So you could say that it's potentially the simplest setting you could look at. So it's like a conditional without noise, it's just a function. So if we assume that now our input is some generic density that is independent of this mechanism, that's our assumption. So the mechanism knows nothing about the shape of this density. That would be the generic assumption. Then it turns out that the density over the effect will know something about the mechanism, because wherever this mechanism, which is just a one-dimensional function, was very flat, the output density had large values. So if we assume independence between cause and forward mechanism, then we won't have the same independence between effect and backward mechanism, or sort of a mathematical backward mechanism, which is not a physical mechanism. And we can formalize that. We can formalize what it means to be independent in different ways. And if we do it like this, I won't go into details, then we can even prove that in the backward direction, this dependence measure with the covariance between these two quantities will be strictly positive. So if it's independent in the forward direction, it will be provably dependent in the backward direction. So we have an asymmetry, and this holds true unless the function is the identity. So in the non-trivial cases, this holds true. Okay, so it turns out this has rather interesting implications, and I want to have a little excursion, just 3 or 4 minutes into physics. And for that excursion, I did a different formalization. So far, I talked about causal models in terms of statistics. So there's a causal structure which implies a statistical structure, but actually statistics is just one choice. And I would argue the causal structure is the fundamental one, because the causal structure captures the physical mechanisms that generate dependencies, for instance, statistical dependencies, but they could be other dependencies. And in this setting here, we instead make these noise variables. They were before random variables. Let's now make them bit strings, and let's make them independent bit strings. Before they were independent random variables, now they're independent bit strings. What does it mean for bit strings to be independent? It means if you concatenate all of them together and you compress them, you don't save space compared to compressing each one individually and summing up the compressions. So here we have a DAG, directed acyclic graph. There's a computer program, UI, which is what before was the noise. And now we think of this bit string as a computer program running on each node. T is a Turing machine, and P, A, J are the outputs, the programs that were run on the other nodes. So it's like a computational graph. And we assume the independence of these programs. And if we do that, then it turns out that this model implies a causal Markov condition, just like the statistical one. So it implies the same kind of conditional independence properties, only that conditional independence is now formulated in terms of this compression notion, or what's called Kolmogorov complexity or algorithmic complexity, instead of statistical information. So that's quite interesting. It shows that this is independent of whether you put statistics on top of it or something else. And if you do it like this, and it's just an excursion, so if you don't follow this part, don't worry, you can join again later. If you do it like this, then there's this nice link to physics. And in this case, we assume we have a beam of particles. So we think of this as the cause, which is scattered at a non-trivial object here. That's our mechanism, this scattering mechanism at the shape of this thing. Then there's an outgoing beam. So these things flying out in different directions, that's the effect. And this outgoing thing obviously contains information about the object, because that's how photography works. Right? The photons that we photograph contain information about the objects. So why is it true that the outgoing beam contains information about the object and the ingoing one not? So why is there this temporal asymmetry? Because physics, we know microscopically, is symmetric. The time evolution is reversible. And the solution is there's an independence assumption. We assume that the ingoing beam is independent of the object. And then as an implication, the outgoing one is not. So it's exactly the same thing as before. And if we formalize that, so we formulate independence between the ingoing thing and the mechanism, now in terms of algorithmic independence, so in terms of compression, then we can prove that the complexity, the Kolmogorov complexity of the state of the system is non-decreasing under time evolution. So that means entropy cannot decrease, it can only go up. And that's what's called the thermodynamic arrow of time. So much for the excursion to physics. Let's go back to statistics and machine learning. So what does all this causality stuff, what does it tell us for machine learning? So the first thing that it tells us, which I still find somewhat surprising, is that it tells us that the causal direction of how the data were generated has an implication for the feasibility of certain machine learning tasks. More specifically, let's assume we have some tasks where the direction of prediction is the same as the direction of causation of the data. So in the generative model of the data, this is our causation. And let's look at some other tasks where it's the other way around. So that's just the simplest two cases, and we've looked at more complex ones, but let's try to understand these two simple ones first. Now, let's still assume our independence assumption. So the probability of the cause and the mechanisms, or the condition of effect given cause, are independent. So one thing tells us nothing about the other and vice versa. Now, we want to do machine learning, which means we want to learn a mapping from X to Y, which means we want to estimate some properties of P of Y given X. Now, one particular task that people are interested in is called semi-supervised learning. So in semi-supervised learning, the idea is, let's get additional unlabeled data so we have more information about P of X, and let's see what that helps us for learning. So how does that help us get a better estimate of P of Y given X? Now that looks suspicious already, right? Because we just made this independence assumption. So it turns out if C is X and E is Y, then exactly the kind of thing that semi-supervised learning seems to need is ruled out by our assumption, which means in the forward direction where X is causing Y and we're predicting effect from cause, semi-supervised learning should be futile. And one can make a similar argument the other way around in the opposite direction. Since we know that in the backward direction there will be a strict dependence in the previous model, is our simplified model, then there semi-supervised learning should be possible. And it turns out for other tasks such as covariate shift adaptation, it's kind of the other way around. So it's harder in the opposite direction, but let me skip that. Now, we looked at that. Initially, we just looked at benchmark studies run by other people, and it nicely lined up that in all the cases, I mean, people were puzzled, sometimes it works, sometimes it doesn't. All the cases where it worked effectively, all the cases where it didn't work, where the causal direction and where it worked was either anti-causal or some kind of confounded setting. And we can also interpret all the assumptions that people come up with to explain semi-supervised learning in terms of links between these two objects. Now, more recently, we've looked at various NLP tasks. We've thought about which of them are causal, which ones are anti-causal, and then also looked at a number of benchmark studies to see if the results are consistent with these predictions. And this also largely seems to be the case. So it's quite compelling that the results make sense. It's not a 100% thing, but it's interesting because it tells us something physical about, you could say it's not just a mathematical statement, but it's about the physics of machine learning problems in a certain sense. So let me skip that. And I think I will also, or maybe I'll briefly talk about that. So when the pandemic happened, we started looking at data, try to make sense of things, also using methods of causality. And one particularly interesting case was this one, which was that you might remember, so it started in China, and then the first European country to be heavily affected was Italy. And Luigi Gresile, who's a PhD student from Italy, he started looking at that data, and he was surprised to see that at some point the case fatality rate in Italy, so the fraction of people who die from COVID was higher than in China, and he was puzzled. I mean, his father is in medicine, and Luigi felt that Italy has a good medical system. So why is that the case? And he started to dig into the data and then looked at the different age groups, and he noticed that within every age group, it was the other way around. Just the overall numbers were like this. And then also together with Julius, another PhD student, what became clear is that this is actually a beautiful example of what's called Simpson's paradox. The difference, of course, can be explained in this case by the different case demographics. So Italy is a much older society than China. So even if in each age group, your chances of recovering were higher in Italy than in China, since in China there are so many more young people, overall, it was still reversed. So this was quite illuminating. And then you can start trying to analyze this in terms of a causal graph. So you can say you have a country which might have an effect on the mortality, but also in the age distribution, and the age distribution also has an effect on mortality. And then how do you tease apart these different paths, which one has which influence, and you can do that. And you can say that then in the beginning of the pandemic, it was actually sort of beneficial for our patients to be in Italy. So the so-called natural direct effect was negative, which means lower numbers. But then as the Italian healthcare system was overwhelmed, this actually also turned around. So this was rather interesting, and is now published in the IEEE Transactions on AI. We had a bit of a discussion. We tried to also send it to an AI conference. We were told this is not AI. And then we told them, look, when we posted it on the archive, then Julia Pearl tweeted and said, well, this is the first beautiful example of what AI can do about the pandemic, but the reviewers didn't consider it AI, the first reviewers. So let me talk about another application of causal modeling in my favorite domain, which is astronomy. I originally wanted to become an astronomer, and this is an exoplanet search, and I'll try to keep it reasonably short. So in this application here, we're looking for what's called exoplanets. So these are, in this particular application, we're looking for them using the transit method. So we look for exoplanets that pass through the line of sight between a star and us. So that doesn't always happen, but there's lots of stars in the galaxy, and then there's still lots of them where the geometry nicely lines up. And while this happens, you should see a little dip in the brightness curve. Now, there are these brightness curves measured by this space telescope, which is called Kepler, which circles orbits around the sun, not about the Earth. So it's on an Earth trailing orbit. It's getting further and further from us away. And staring at a particular patch of the Milky Way, not anymore, but in those days it did. And then take these light curves. And what was interesting was that these light curves of one star, so this is different pixels that belong to the same star, they look surprisingly similar to light curves that we would get by looking at another star. So there's some that go down, some that go up. So that means there is some shared information between these light curves, which is surprising because the stars are light years apart. So the only explanation for the shared information is that they are measured by the same instrument. So there's this confounder which influences both measurements of stars. So each star is influenced both by the astrophysical signal and this confounder. And now the interesting question is, can you somehow get rid of this confounder and get closer to the astrophysical signal? So can you remove this confounding instrument noise. And it turns out there's a very simple idea that can be mathematically analyzed, and it works rather well. And the idea is that we try as best as we can to explain a given star in terms of other stars of which we know they're independent, but they share as many characteristics of the noise as possible. So we compute the best explanation of this star in terms of the other ones, or in terms of many other ones, because actually the instrument measures hundreds of thousands. And then we sort of take that out, that piece that we can explain, and we're left with something which, under certain assumptions, is provably close to this thing in the sense of subject to suitable additivity assumptions. We can prove that the thing that we reconstruct is up to a constant offset, almost surely identical to this thing. So these two random variables are essentially the same. Yeah? So using this, we worked together with astronomer. We found a bunch of exoplanets. I was very happy about that. They got different names once they were confirmed. One of them was called K218b. And then it turned out that 1.5 years later, I read this news also, but I didn't make the connection. I didn't remember that this was one of our exoplanets, but then the astronomer alerted me to it. It turned out it was the first exoplanet where people found water, the first exoplanet in the habitable zone around their host star, allowing for liquid water, such that they actually did find water using methods of spectroscopy. So that was a very happy coincidence. So in the remaining time, so I think I'm aware I used up some time at the beginning. My clock says 34 minutes, so I hope I can still use a bit of time to talk about how to bring things together now and talk about what one could call causal representation learning. Because I have, I've criticized machine learning a lot. I've shown examples where it fails, and I've argued that the culprit of its shortcomings is this reliance on the assumption that the data comes from a fixed distribution and there's no interventions and no changes are possible. So this AIDA assumption. But and I've argued that causality can address this, because a causal model sort of models a whole family of distributions. It can talk about changes, interventions, etc. So that's all fine. Unfortunately, by moving to causality, we have kind of reintroduced one of the weaknesses of symbolic AI, which machine learning was trying to address in the first place. So maybe we've thrown out the baby with the bathwater. And to just discuss this a little bit, let's go back in time again to Herb Simon. So, in hindsight, we're always, we think we're more clever. It's the same as with this neural network tank urban legend. Things in hindsight are simple, but if we now think of classic AI, maybe we could say, well, it was a little naive to assume we can realize intelligence explicitly by programs written by humans, because one could say the existing examples of actually intelligent systems, like our brain or the brain of animals, they appear much too complex for that. So that's one point. But maybe the bigger point, or second problem, is the question: where do the symbols actually come from that we are going to process? Who gives us the symbols? Because we live in a high-dimensional world, and nobody labels the symbols for us. And that's this problem we also have in causality. So in a way, we're faced with two problems, and it seems like we can't solve both of them at the same time. And one could say the core problem of statistical representations, as learned by modern machine learning, is that these representations only include statistical information. So they don't capture interventions, reasoning, or planning. And the core problem now of causality, the way it's developed so far, is that these structural causal models are usually formulated at the symbolic level. So they assume the causal variables are already given. So we have a problem here. How do we solve both these things at the same time? How do we automatically learn these representations? And I want to end with maybe 5 minutes of general thoughts about that, and then just a few quick examples and pointers to literature where you can read more if you're interested in this problem. So I told you there's this nice factorization of a joint distribution in terms of the causal mechanisms or in terms of the causal conditions. That's the factorization that respects the causal graph. Let's call this the disentangled or causal factorization. And let's call it the disentangled one with the additional assumption that not just do we have this factorization, but also that these objects are independent mechanisms in the sense that we can independently intervene on individual ones of them. So we can change one of them without automatically changing the other ones. So if we change one, the others will remain invariant. Now, as a special case, of course, if the graph is disconnected, if you have no non-trivial structure, dependency structure, then you will get something like this. Then this just reduces the statistical independence. But I think the more interesting case is where they are dependent, because the objects in the world do have dependencies, even if they're separate objects. And now, if this is the disentangled factorization, there's also many factorizations that are not disentangled, but mathematically possible. For instance, mathematically, you can write down this factorization, and you can do this for any permutation of the indices. So many possible factorizations of a joint distribution, but they're not as nice as this one, and they tend to be higher dimensional than this one. And you cannot make interventions on, usually you cannot assume that you can separately intervene on this in the sense of, is there an intervention in the real world that in a system will selectively lead to an intervention on this conditional? That will usually be not the case. And also, if you intervene on one of those physical mechanisms, then in this representation, typically all of these guys will change at the same time. So they are entangled with each other. Now that has an interesting implication for the problem of distribution shift. Because if we write a problem in the disentangled factorization, it would be reasonable to assume that a small distribution shift will manifest itself sparsely in this representation. So only a few of them will change, but not necessarily all of them. Whereas in the entangled factorization, whatever you change, everything that's changed will be distributed across all terms. So therefore, looking for sparse changes should be a sensible inductive bias to look for causal variables. So that's one possible way of looking for causal variables, or looking for causal representations, causal training, you could call it. So you exploit this sparse mechanism shift. You can also try to encourage independence of mechanisms. You can try to look at interventions, or what's called counterfactuals, which is a type of intervention. And I'll show an example of this also. And finally, you can also try to embed directly the structure of a structural causal model into a neural network. Specifically, we've worked on embedding it into a decoder. So, just in terms of the time, we don't have much time left, so I will just give you pointers. So about the last thing, so that we have some work on something we call the structural decoder, where we embed a structural causal model architecture, and we get to systems that, even though we don't explicitly regularize the latent space, we get a very nice quality in terms of both reconstruction error and something called FID score, Fréchet inception distance, which lower is better. And for this one also lower is better. So these models, these structural models are the green ones down here. So that works quite well. As a second project I wanted to mention is this now trying to directly encourage independence of modules in a neural network. And this architecture of so-called independent mechanisms. So this is an architecture where we train the system on data which has been corrupted by different degradation processes, but they are not labeled by which process corrupted each one of them. And then we have a competitive procedure where different modules compete for data and try to undo these transformations. And whenever one of them does well on one example, then it actually gets a gradient back by scoring this example with against a discriminator, which is trained like in a, so the overall thing is like a gun. So it tries to generate samples that are not distinguishable from the canonical examples. And then overall, they start specializing these experts on different degradations. And in the end, each one of them has captured one of them. And it works quite well, both in distribution and out of distribution. So if you apply these things a different kind of data, these mechanisms actually turn out, they transfer, for instance, here to these omniglot characters. And more recently, we've generalized more or less the same idea to a recurrent setting. Second example, now we're talking about interventions and counterfactuals. So this is, here the idea is we want to find modular representations in generative models. And basically the idea is to cluster neurons that are somewhere hidden in the architecture that jointly control certain aspects of an image, in which we should thus be manipulating jointly as a bunch. And then we manipulate them using something we call hybridization. So which means we take a bunch from one that corresponds to one input example, and then sort of graft it into the latent representation of another example, or mix it, sort of combine it with a different bunch taken from another image. In this way, we can generate what one could call counterfactual examples, where certain things are different, but all the rest is kept the same. So for instance, we can take this image of a chicken and then make this intervention, which leaves the chicken more or less invariant, but changes the background. Or we can take two real images, the left and the right are real images, combine them in the latent space and generate a completely synthetic image, which in this case, that's a koala, that's a teddy bear, looks a little bit like a koala teddy bear. And so we're trying to apply this idea of interventions also to explain other methods that have recently become popular. For instance, this in this area of self-supervised learning, there's this SimClear method, which tries to learn representations that are insensitive to certain so-called image augmentations. So here we have image augmentations applied to the same sort of semantics. So the object is always a dog. So an augmentation changes some aspects of the image, but while leaving invariant that there's always a dog in this image. Right? And now we can write this as a causal latent variable model, where we assume there's this invariant content, but there's also the style, how it's represented. And then we can prove that using suitable data, which consists of pairs of images, augmented images, we can actually identify, and this is a nonlinear setting, we can identify up to certain indeterminacies this invariant content, which is assumed to be there both in the original and in the augmented image. I think that's about all as much I should say now, given the limited time. That's a kind of training data that's the same object in different views. And yeah, and we have identifiability results for different settings here. Okay, I think I'm going to skip this and this one also. Maybe if someone asks a question, I can come back to it later. Maybe briefly mention that we've also started applying this in robotics and started collecting robotic benchmark data. Because this is very nice, because here we have precise control over the causal variables, and we can make interventions, and we can use this also to study robustness in transfer. So this in various settings, for instance, the transfer from simulations to realistic data. And we can look at things that like out of distribution, generalization of downstream tasks, etc. And ask the question whether disentanglement is a good predictor for robustness, etc. And this is so this is a project also, just as a pointer, which is a robotics project which is inspired by this independent causal mechanisms principle. And here we have another robotics project which is about causal influence detection. So if you think about causality in a dynamic setting, then like most of the time, or the causal interactions that happen in the real world, they are relatively sparse. Like if you have a gripper, most of the time the gripper does nothing, it cannot interact with the world, but then once you are close to an object, it does have a causal influence. And if you can detect these things, then that can influence how you do reinforcement learning. Yeah, so maybe, okay, I think this might be the last one, or the second last one, so maybe I can take just 1 minute for this one. Give me a signal if you think I'm horribly over time, but this one is quite a cute project, so maybe I can briefly speak about this. So this is about the problem of nonlinear ICA. So we assume that the observed data is a nonlinear mixture of these two signals here. And we assume that these sources are independent. Now in linear ICA, knowing that these sources are independent and assuming that this forward mapping is linear is sufficient to identify these two sources under certain assumptions and up to certain indeterminacies. If, however, this mapping, the mapping from S to X, this function f is nonlinear, then it turns out this problem is very hard unless you have auxiliary variables, etc. Now we are going to try to make this problem easier by not just assuming this independence between the sources, but assuming an independence of the mixing process, so an independence on the level of mechanisms as opposed to just a statistical independence of sources. So that's a bit like in the ICM principle. Unfortunately, we can't apply it directly because normally in the ICM principle, we have a cause distribution, we have a mechanism, the condition of effect given cause. We assume these two are independent from each other. Now, in this case, we don't see the cause distribution. We want to reconstruct the cause distribution. But we can do something slightly different, which means we do something at the level of the mixing function, which intuitively can be interpreted as saying the positions of the speakers are not fine-tuned to the room acoustics and the microphone placement. And if we do that, and we can write down a certain quantity, a certain contrast function that corresponds to this, a certain orthogonality condition on the columns of the Jacobian of this nonlinear forward mixing process, then it turns out that this both works on certain examples, and it removes certain sort of spurious ICA solutions, certain mathematical constructions that are normally used to argue why nonlinear ICA is not identifiable. So that's, I think, also quite an interesting direction. And now the last thing is about visual scenes. So here, we can, I mean, I always find it useful to think of generative models as causal models. And obviously, if you think of a scene has a generative model, and you have some objects, they have intrinsic properties, they have a position, orientation, there's lighting, which affects multiple objects, etc. So you can think of a complex causal graph generating an overall scene. And you can think of this as a disentangled cause factorization because you can intervene on objects separately, etc. And now you can ask the question, how do we generate scene models that have this kind of causal structure? Because traditionally, people just take a big gun and train on huge image sets, and then the gun has to learn all this variability and how many people to put on the image and how to relate them to each other. That seems very wasteful to just try to sort of drown everything with data. And we started working on this problem about 2 years ago. And now we have a pretty nice system where we have a training set that consists of videos from an artificial aquarium scene. And then we identify objects from that using effectively what psychologists call the common cause, a common fate principle. So things that pixels that move together belong together. We find object candidates, we train object models in a robust way with augmentations, etc. And explain the scene in terms of object and background. And afterwards, we get a model where we can sample new scenes. We can intervene on things like the number of objects, the fish identities, the position of the fish, etc. So we get a causal generative forward model for such scenes, which is automatically learned in an unsupervised way from this kind of data. So let me conclude, since I'm at the 50-minute mark now. So the overall goal of our research is that we want to move from statistical representations towards what one could call world models, or maybe a more fashionable term recently is the term digital twins. So you have some phenomenon in the real world that you want to map into the computer, and you want to map it in such a way that maybe not just the statistics are preserved, but other aspects as well. And Because you could have a full differential equation model, and maybe that's what most digital twins try to do, I don't know. But that seems very expensive and difficult, whereas a purely statistical model maybe doesn't help you much because you cannot do interventions. So we probably want something in between, which supports notions of intervention. We want to, this thing should have several properties that I think will be beneficial for the future of AI and machine learning. It should be data efficient, because we don't want to train a new model every time we have a new problem. So we have to be data efficient and be able to pool data from multiple tasks in multiple environments, just like animals and humans do. We use all the data we can get, even if the tasks are different. Now, for this to be possible, I would argue that the models have to use reusable components that can be repurposed across different tasks. And maybe not every component works everywhere, but maybe most components work in multiple places. And a good inductive bias for such components that have some generalization is that they could be causal independent mechanisms, because the world is probably modularized into such mechanisms. So that's the one aspect. The second aspect is these models, world models, should be interventional, in the sense that they should allow a notion of intervention in action. And I like this quotation of Konrad Lorenz. Konrad Lorenz was an Austrian ethologist, so studying animal behavior. And he said at some point in a book, this book here said effectively something like, thinking is nothing but acting in an imagined space. So if you have an imagined space which is interventional, which supports actions, then you can start performing thinking in this sense of ethology. You can perform planning, reasoning, and do things that animals do. And so if you're interested in this general direction of causal representational learning, we recently wrote this overview paper, which is available online, toward causal representational learning. And so I encourage you to go there. And maybe if you allow me a final plug, since I think many of you are PhD students or maybe thinking of doing a PhD, please think about maybe connecting to the Alice PhD program, which was started recently, which is going very well, and which effectively has started sort of putting this large spider web on Europe, connecting many, many places to each other. So we have 120 elites PhD students by now, and they're supervised by 116 different advisors. So there's always pairs of advisors in charge of one student, usually in different countries. So that's all I wanted to say today. Sorry for the technical problems at the beginning, and thank you for your patience. And thanks to all my group contributing to this work. And I'm happy to have some discussion with you now. Thank you.